All right, so what I've just written down right here is first summarizing acids, an equation for acid dissociation, aka acids behaving like acids, right? The behavior of acids is defined by increasing H plus or hydrogen ions in solution. So HA separating into H plus A minus, that is acid dissociation. That's acid behaving like an acid. The equation right below, what differences do you guys observe between these two equations?
Uh, it,
I didn't really catch that. I don't know if it's the volume on my side or something, but
oh, sorry.
yeah.
Yeah. Does it create a base?
Yeah, that's like super soft for me. Hold up, say that again. I'll turn it all the way up.
Sorry, I was using the wrong mic. Does it create a base? Or
Yes, that was very loud on my side, but you were saying, yeah, it creates a base. Um, both of them create bases. A minus here, that's going to be the base, right? Larry says acid plus water. Yeah, basically the main difference between these two is that there's a water existing here, and then the water is what is absorbing the H plus. So then we have this thing called H3O plus, hydronium ion. We talked about this, I think 2 weeks ago. Anyway, I brought up this second equation because it's a way that some people represent acids, because H plus does not actually exist in solution. It doesn't exist by itself in solution. H plus is very unstable of a molecule, and it's just it tends to bind to other molecules very readily. So that's why in water it actually forms H3O plus. So the second equation is technically more accurate, you could say. The thing is, you can simplify this equation to this, and all the math is the same, all the behaviors are the same. And that's why usually you will see acid equations written like the top one. The bottom one is something you might observe. So I'm bringing this up because when you see this bottom equation or something in the form of the bottom equation, don't be alarmed. It's the exact same as the top. They say the exact same things about acid behavior. All right, down here, I'm going to box this. Down here, we have our generic acid equilibrium expression. So K, that's going to be our acid constant, acid dissociation constant. But isn't this is Larry's question, but isn't the definition of an acid is that it has H plus, not that it has H plus, that it produces H plus in solution. So things that have H plus are the ones that tend to produce H plus in solution, like HCl. When you put it in water, it separates H plus, Cl minus. That's adding H plus to water. So that's an acidic behavior. There are compounds that, no, pretty much every compound that adds H plus to water, it already has H plus. The thing is, compounds that have H plus are not necessarily acidic. Like for example, NH3, ammonia, there are H pluses attached to an electronegative N, but this is a base, not an acid, because you can't just go based on whether it has H plus or not. It has to be an acidic proton, and there are those are more specialized, I guess you could say. Anyway, this acid equilibrium expression, just as we've talked about with equilibrium, the constant, which is K, that is something that's unique to each reaction and doesn't change with concentration. So that's why we can write this relationship out, and we can use it to find how the acid or the conjugate acid or the conjugate base behaves in solution. Like how much do we have when this thing happens, so on and so forth. All right, looking down here with water forming H plus and OH minus. So what's going on here is basically I plugged in something for A. So what did I plug in for A?
OH minus.
OH minus, yeah. OH or OH minus. OH minus is what I plugged in for A. So basically, up here, A minus just represents the conjugate base, right? The conjugate base of this acid, HA. OH minus here is the conjugate base, and the acid that we're working with is water. And water, of course, is not a very acidic compound, but here we're writing it as an acid to see what this equation is about. So here I write this equilibrium acid expression. All this stuff looks pretty normal, except that there's something that we can do with this equation, something that's technically, I guess you could say, wrong with the equation. And does anyone know what that is? I'll give you guys a hint. It has to do with this term.
It has to do with what? Sorry, you cut out.
I'm sorry, Amos, now you're a little bit soft. Say that again.
I said you said it has to do with what?
It has to do with the H2O term, the one I just circled right here. There's something wrong about that term.
Isn't it zero because it can be found in nature?
You're on the right track, but it's not because it could be found in nature. It's because in equilibrium expressions, you don't include liquids and solids. They don't behave the same way as they don't behave the same way as aqueous or gaseous substances. So this term does not exist. There are some cases where people say, oh, the molarity of water for water is 56 molar. Some people say that. And if you guys remember molarity, usually we work with 1 molar, 2 molar, or 0.1 molar, 0.2 molar. 56 molar means it's heavily concentrated. And that's because people are talking about water in itself. Like, what is the density of water if you just have water by itself? That is, yes, you could say it's 56 molar, but it's not something you put in your equilibrium expression because that is the solvent that you're working with, and it doesn't interact with it doesn't change the equilibrium in the same way as scarce compounds like H plus or OH minus. It doesn't change that in the same manner. So that's why we take that out of our equation. By definition, the way we define K and all of that means that this term doesn't exist here. So what that means is we can then set this equal to just the numerator. And this is actually a very special expression. This is what's called not Ka, but Kw, W for water, of course, because it's a very special equilibrium constant. Kw, which is equal to H plus, OH minus, it's actually going to be equal to 14. And what is significant about 14? I want to see if anyone, this is a bit of a harder question.
Oh, I think at like 25 degrees Celsius or something, they that's the pH scale basically, I think, or something like that.
Yeah, you're on the right track.
So the concentration of those have to add up to 14.
Yeah, what I was looking for is that 14 is 2 times 7, and 7 is the neutral on pH scales. That is significant. It's the most basic. Yeah, you could say it's the most basic pH. Basically, what this means is, how do I put this? Let's say I have, yeah, basically, if we think, sorry, what I said right here is actually kind of wrong. So let me fix that real quick. This is not 14. What I meant to say is that this is 10 to the power of negative 14. And the reason why I said 14 is because if you think about how pH works, it's negative log, right? We mentioned that last time. So let's say I have an H plus concentration of 10 to the negative 5th molar. That means that the pH could be equal to the negative log of that value. And this is log base 10. Negative log of that, which would then be equal to 5.
Just the exponent.
Yeah, the exponent, but then you have to take the negative, so then it becomes positive. So yeah, 5 is going to be our pH, that's acidic, blah, blah, blah. Basically what it's saying is that if you take the H plus molar concentration, multiply it by the amount of OH minus you have, also in molar, you get 10 to the negative 14th always at 25 degrees Celsius. And if that seems like a confusing relationship, why does it behave that way? It behaves that way just because of the same way acids behave with equilibrium. That's like when you have more of one compound, then it reacts with the other and therefore decreases the other value. Both the values decrease a little bit, but then it balances out overall to become the same product. Same thing going on here. And this is useful because it allows us to easily convert between H plus and OH minus. So let's keep up with this example. H plus concentration is 10 to the negative fifth, so pH is 5. Now, using the relationship of Kw, could someone tell me the OH minus concentration of this particular solution?
10 to the negative 9.
10 to the negative 9. Yeah. So basically, since you have more H plus, you're going to have less OH minus. And remember that if this doesn't make sense, it's like, why doesn't the H plus react with OH minus? Because this is equilibrium. Most of the H plus has reacted with the OH minus, right? Water exists. Water is the product of H plus and OH minus reacting. But this is a dynamic equilibrium, so that just as it's reacting to form H plus, H2O, it's also separating at some rate. And of course, this rate is very low, and that's why all these values are very low. That's why we have 10 to the negative fifth, negative 9, things like that. But that's the dynamic equilibrium that's existing right now. All right. So we never really went molecular with our analyses of H plus and OH minus, mainly because it's more tedious. And I think it's going to be harder for me to talk about over Zoom, and it's just not good. But I hope it kind of makes sense why this would work. Let's say you add H plus into solution. Some of that H plus is also going to react with residual OH minus or react with H2O, but you have a net greater H plus, and therefore that balance is shifted. Instead of being 7-7, you're shifted off a little bit. All right. Anyway, I'm just going to write the P something for this. I'm basically going to do the same operation of negative log. This is what's called POH. Essentially, it's the same thing as pH, except that you're dealing with hydroxide instead. So it's going to be that. What is that value? So what is the POH here?
What's the pH? Is that
POH.
what you asked?
Yeah. Am I glitching or do you guys hear me?
I think you're fine. I'm just hearing it wrong with my
Oh,
headphones.
that's no problem. Yeah, Larry, you got it. It's 9. So once again, pH and POH. Another way of writing this top expression would then be pH plus POH is equal to 14. So I'm going to write that over to the side a little bit. pH plus POH equals 14. That is an equivalent expression for that. So that's the behavior of H plus and OH minus. Essentially, this is just another relationship that we can use in our calculations. And just taking another specific case, let's say we have water, just like regular pure distilled water at 25 degrees Celsius. And this relationship, of course, still applies. 10 to the negative 14th. What would be my H plus and my OH minus if this is pure distilled water?
7 and 7.
7 and 7. So that's why we have 7 as neutral, because of this relationship, because we know this applies. The OH minus would also have, so the POH of pure water would also be 7. I'm going to go on a quick tangent though, because I think it's important to bring up. Let's say, you notice how every time I talk about these things, I say at 25 degrees Celsius. The reason for that is because K changes with temperature. We've talked about that before. The way reactions occur, right? Collisions, reactions are just basically atomic mini collisions, right? Many mini collisions happening at once. Basically, when the temperature increases, the way those collisions happen, so their frequency, the energy with which they hit, all that is different. So therefore, equilibrium is different, and that's why K changes when you change temperature. So what happens when you increase temperature is actually the K increases. So now let's say I increase the temperature from 25 degrees Celsius and say now the K is 10 to the negative 12. Now I don't know what this temperature that would make this happen. I don't know what that temperature is because the relationship is way more complicated than it really appears. Depends on a lot of other factors like activation energy, well, not really activation energy, more change in enthalpy, and there's like a whole development to it. You guys could, if you guys are interested, you could search it up. It's called the Arrhenius equation. I'm gonna put that in the chat in case you're interested in looking at it later on. Arrhenius equation. All right, so anyway, I increase the temperature in this example. Kw is now 10 to the negative 12. Now, what is pH in this case? This is still pure water. And when I say pure water, that means that H plus and OH minus are equal. So what would my pH be?
6.
6, yeah. And we have POH also equal to 6. Now, my pH is now less than 7. So does that mean I have an acidic solution?
No.
No, okay. Larry says yes. So we got a split of answers. Amos, you want to add your own opinion?
Yeah, it is.
Okay, Amos says yeah as well. All right. I'll take it from the opposite side. POH is less than 7. Usually when POH is less than 7, that means you have a lot of OH minus in solution, and that would imply that your solution is basic. So does that mean the solution is basic then?
Wait, can you repeat that? Sorry.
All right. So pH is less than 7, which kind of seems to imply that the solution is acidic. But if we look at POH, it's also less than 7, and therefore you have more hydroxide than normal, and therefore it would imply the solution is basic.
Oh,
right?
okay, yeah.
Okay, so basically, Angelina's right. The solution is not more acidic. It's still neutral because pH and POH are equal. The 7 reference point only applies in 25 degrees Celsius. Now, that's why most of your problems you'll run into, so like, I don't know, AP and USNCO, they're all going to say that, they're all going to implicitly say that temperature is 25 degrees Celsius. If they change it, then you need to account for this. But remember that pH equals 6 doesn't fully justify a solution being acidic. You have to see the other side of it. How does it compare with POH? Then that would determine whether it's acidic. It's very funny because I'm not sure if any of you guys do Science Olympiad or have heard of it, but I've done Science Olympiad Chem Lab a few years now. 10th grade was a glory year for me and got 5 gold medals. So it was very exciting. One of the questions they asked in the UPenn competition, we got 5th that time, which was not as good, but one of the questions they asked was about this topic. Increasing temperature, does that mean your pH is now acidic? And the answer is no. Larry, no, they were not international. I'm not a pro. I'm not a pro gamer. I do not go to national because you guys are in New Jersey, right? Yeah, in New Jersey, I did get Golden State, but the other ones were invitational. So Yale, MIT, places like that. So yeah, they were technically national. Anyway, this is too much about Science Olympiad. Basically, there was a question like this and it got many people. So watch out for that. I did not just do Chem Lab. I also did Sounds of Music and Write Stuff. Those are my things. We can talk about Science Olympiad later. Anyway, I want to talk about this because one of the first questions that we're going to talk about today is going to be talking about this, or at least it's going to utilize this particular fact. Now, what I want to do today is kind of synthesize some of the things we've talked about in previous classes with chemistry and kind of put them all together in problems. So I'm now going to share my screen with a problem. I'll zoom up a bit. I know it's a little small. This one is just for starters. Harder ones to come, but basically, I think let's take like 2 minutes, try your hand, see how far you can get. If you do get like a final answer, private message me the answer. Do not unmute and tell everyone the answer. I'll spoil the question for everyone else. Just send me a private message and then I'll check it out. After about 2 to 3 minutes, we'll check in and see what our progress is and talk about it together. All right, so far received one answer. Is there anyone who's very close to solving it? Because I don't want to interrupt anyone who's close. If not, then let's move forward. All right, so yeah, let's start moving forward. All right, first thing about this question, one thing I kind of like about this question, that it demonstrates a bunch of key points, not just about like solving questions like this or the chemistry, but also about like problem solving. First thing I want to point out, what is the pH of so-and-so solution of this? The Ka of this is that. All right. Now, when I see this, when I see this particular compound, what I see is there's Na and there's Cn. Cn here, because there's HCN over here, we know that's an ion. It's a like a polyatomic ion. It's like SO4 2 minus. It's a group, Cn minus. All right, so that means that NaCN is essentially just composed of Na plus and Cn minus. What that tells me is that Cn minus is going to be what's actually going on here, what's actually interacting in this particular reaction. Na plus is not involved in this reaction, it's a spectator ion. Na plus is kind of just there to deliver the Cn minus. That's some way you can think about it. All right, Cn minus. Now tell me, does that have a hydrogen ion on it?
No,
NaH?
but
No.
with the HCN, is it a base?
With HCN, there is a hydrogen and it's not a base. So let's talk about it a little bit. Cn minus does not have a hydrogen, therefore it cannot be acidic. The whole
Wait, so
point of,
oh, okay.
yeah. As we talked about with acids and bases, HCN should look like the conjugate acid to you of Cn minus at this point. Hopefully we can recognize that now. Add the H plus, so up the charge 1, add the H on. HCN is the conjugate acid here. HCN is going to be the actual acid. Cn minus is a conjugate base. And opposite way, HCN is the conjugate acid of Cn minus.
Wait,
Make
so
sense?
is Cn minus a base then?
Cn minus is a base.
That's what I meant. Sorry if I.
Yeah, no problem, no problem. Everyone, is that clear with everyone? This is something that when you become really experienced, you see that all in 2 seconds when you see this question. You see NaCN, you see HCN, you're like Cn minus HCN, conjugate acid base. All right. So knowing that this is a base now, what is the pH of a basic solution? pH of a basic solution. First of all, is it greater or less than 7?
Greater.
Greater. All right. That's A and B out of the window already. 2 answers taken out. This is like if you got 2 answers taken out, if you got half your answers taken out on Jeopardy, you'd be in such a good position. AKA, you can eliminate 2 answers from this question right away. That's fortuitous, you know? And that also means that Larry's answer of C is still in the running. So we'll see if that's correct. Anyway, so 2 answers gone. That's test taking strategy. That means you can get a 50% guess rate on this right away. And that's honestly pretty good if you really didn't know how to solve this question. Now, if you didn't know how to solve this question, it might be a problem for trying to do well. But anyway, let's keep on going. Now that we have these 2 compounds, what we can do is write out the acid dissociation equation. And remember, acid dissociation equation means we take the acid, HCN, and then we say the H plus separates and we have the conjugate base. So can someone help me write that out? What is the acid dissociation equation? First, start out with the acid.
HCN.
HCN, okay. And then what comes next?
Times Cn minus.
Times
Are we
Cn.
doing the concentration stuff?
No, we're writing out an equation, like a reaction equation. Remember, we have HA goes to H plus plus A minus. This is essentially what we're rewriting, but in this particular case. So Amos, you start out with HCN. What do you write next?
Oh, H plus.
All right, I'm gonna say goes to H plus and
Cn minus.
Cn minus. This is going to be our acid dissociation equation for HCN. Yeah, Larry, yours is slightly off. I hope you see what we're doing here. how the Na is gone, first of all. Yeah, all right, cool. Does it make sense with everybody? How I took the compounds we have and made an acid dissociation equation.
Yep.
Yeah, all right. And from this, now we can construct our equilibrium. So I'm gonna then write Ka equals, draw a line. And remember with these products on the top, reactants on the bottom. All right, so can someone tell me that? What do I write? First, starting with the numerator.
Concentration of H plus.
Yeah. And
Concentration of Cn minus.
yeah. What else?
And then HCN on the bottom.
HCN on the bottom. All right. We move and that is going to be our acid equilibrium expression. All right. What is the pH of this? Okay. So going back to this actual question, we're dealing with a Cn minus. We're dealing with a base. So we're not actually going to be using an acid equation. We're going to be using a base equation. And now that we have the acid equation, it's going to be very easy to do the base equation because, and I'll show you guys what we can do to kind of transform the equation into base. Anyway, we have this, right? So I am going to express the base side of that, the flip side of it. All right, so say, I'm just gonna put it down for now, and then we'll follow along later. This is going to be what's called a base equation or base interaction equation, base whatever you want, base equation essentially. Just as how the acid equation describes acidic behavior, the base equation describes basic behavior. So what do you guys see here? What I see is that you took the base and the acid and you flipped their sides. Acid is now a reactant, base is now a reactant, acid is now a product. And then what's going on here is that the base is removing an H or an H plus from H2O and thereby forming a hydroxide. That's going to be a key characteristic of any base equation. You form hydroxide from water and then the base forms the conjugate acid. So here in the acid equation, acid forms conjugate base and the product you have is H plus. Here, base forms conjugate acid and you have hydroxide as your final thing. So far, so good?
Yeah.
All right. Now let's try for this specific case. All right, hit it. What are we writing first? We're writing out the base equation.
Cn minus.
Yep. Keep on going.
Plus H2O
Keep on going.
goes to HCN plus OH minus.
Right on the dot. That's exactly it. That's going to be our base equation for Cn minus. All right. Another key point I want to bring out. First, I'm going to erase these top parts. All right. And I'm going to. All right, never mind. I'm going to shift them separately. Hold on. Let me think. How do I want to do this? All right. We'll do that, and I'll do that. So basically what I've done is I put these two equations on top of each other so I can emphasize one point. Let's say I add these two equations together. So I'm just going to draw a little plus. Okay. now that means that I have HA and HA on both sides, so I can cancel those out. I have A minus and A minus on both sides, cancel those out. What we're left with is, surprise, surprise, the water dissociation equation. That's just to emphasize that the acid equation and the base equation are flip sides of each other. They're opposites. They're like character foils. They contrast each other. Add them together, you receive neutralization. So that's another way you can kind of figure out the base equation from the acid equation. You just look for neutralization. So here, acid just separating, producing an H plus. Here, OH minus is produced because the base is taking an H plus. All right. So now what we're going to do is express KB. KB just being the equilibrium expression for a base. I'm going to write that down. KB equals something. And this is still an equilibrium expression. So that means we can still express this as products over reactants. Now I'm going to take this and move it down here. Now tell me the products and reactants of this. I'm going to draw the line first. All right.
OH minus.
Hold up. OH minus. Wait, actually, give me one sec. I took the wrong equation. I meant to take that. All right, keep on going. My bad.
HCN, shouldn't it be
HCN. Yeah.
divided by
And
the
then-
concentration of H2O and Cn minus?
All
But
right.
H2 doesn't count, right?
Exactly.
Oh yeah, H2O doesn't count.
H2O doesn't count. Yeah. Good catch, guy. So we have Cn minus on the bottom. Cn minus. Yeah, there you got it. So, all right. Another thing I observe here is if we multiply these two Ka, the Ka and Kp expression. Now, as you guys can probably tell by this point, there's going to be a lot of patterns going on. A lot of patterns going on. Let me try to get this whole equation right. Come on.
You just get water, right?
All right, well, first, hold your horses. Let me try to figure out how to do this. There we are. Pretend that's multiplication, okay, guys? All right, so that's Ka times Kb. Hold up. Zoom whiteboard is not the greatest. Ka times K, Kb times Ka, Ka times Kb. All right. These two multiply together. As Angelina already kind of predicted, stuff cancels out. And what we're left with is once again, water. And it's a very familiar equation. So what is that equal to? Remember we had a very specific name for it. It was K sub
KW.
KW. There we are. So KW equals all that. Now this means we arrive to our next big point. Ka times Kb equals Kw for every single acid and base. Every single acid and base, as long as they're conjugates. So some base and its conjugate acid, if you take those Ks, multiply them together, you always get Kw. And Kw, we know, at least at 25 degrees Celsius, we know for sure 10 to the negative 14th. Oh, shoot. There we are. 10 to the negative 14th. So acid times conjugate base equals water for all chemicals. Yes, Larry. But when you say acid, you mean equilibrium constant for an acid, equilibrium constant for a base, all that. And yes, it equals 10 to the negative 14th. All right. So now the problem's becoming a little bit clearer step by step. They give us Ka, but we're dealing with a base. How do we use Ka to deal with the base? We use this particular relationship. We can solve for the the Kb of Cn minus by using the Ka of HCN. All right, let me just erase this real quick. And I'm not sure if you guys have your calculators, but if you want, take those calculators out. And let's quickly calculate this Kb. So let me write this down again. Ka times Kb equals Kw, which equals 10 to the negative 14. So that means if we're looking for the Kb of HCN, we just take 10 to the negative 14, divide that by Ka. And that gives us, does anyone have it already? I'm not sure. Let me do it myself real quick. We have 2.04 times 10 to the negative 5th. That's what I have. All right. One quick thing I want to note though, actually about this. Notice that the Kb is higher than the Ka. Right, Kb is higher than Ka. Does anyone have a sense for what that means? In
It's
terms of,
basic.
well, yeah, of course, a base is going to be basic, but an acid is going to be acidic. But what I mean is, does that say anything about the relative strength? So Cn minus versus HCN, which one's stronger at what they do?
Cn minus.
Cn minus is a stronger base relative to HCN being an acid. HCN is acidic to a certain degree. Cn minus is basic to a greater degree, essentially. All right, and then if we think about, remember we had that line saying base, acid, remember, and then there's water in the middle. We had like, well, no, this doesn't really apply here. Never mind. Scratch that. Scratch what I said. Let's keep on going with this question actually. So now we have Kb. And I believe we wrote a Kb expression already. So let me just move that over. Putting down
I have a question.
Yep, go ahead.
So wait, did you just divide 10 to the negative 14 by 4.9 times 10 to the negative 10?
That's exactly what I did. Yeah. I'm just moving this back down. All right. Now we do the actual math. But first of all, we have to figure out what can we plug in here. The key, of course, is in the remaining information we have. And that remaining information is this. That's a terrible color, hold up. Is this. The 1.0 was 0.10 molar. What does that tell us? Which of these three chemicals down here is 0.10 molar?
Cn minus.
Cn minus, yeah. And it's stated in the question though. What is the pH of a 0.10 molar solution of NaCN? And remember, Na is not participating in reaction. So really it's just Cn minus. We have 0.10 molar of Cn minus. Of course, this is only upon insertion. Remember, the second you insert Cn minus, it's going to react with water, do its basic thing. It's no longer going to be 0.10. But if you guys think back to the rice table we did a while back, remember with the reaction, initial, change, end, the initial here is 0.10 molar. So this right here, that's 0.10 molar. We're not going to do the full rice table today because it's really more of a beginner, like starter kind of way of thinking about it. And you can easily expedite the process as we will work through right here. Basically, I'm just going to write, and I'll write out what the equation will look like. and then we'll talk about why it is this way. 0.10 molar minus X. All right, so what the heck did I just write? Basically, we start with 0.10 molar, right? That's how much Cn minus we start out with. But it reacts. So we're going to lose some of it. All right, so if we're going to lose some of our Cn minus, hold up, let me move that equation down here. We're losing some of our Cn minus. What are we forming from that loss?
OH minus and HCN.
Yeah. We're also losing water, but remember we have 56 molars or whatever of water. We have a lot of water. It's not a problem. It's not in our equations or anything, so don't worry about it. HCN, OH minus, that's what we're gaining. So that's where we can have our variable, the change in these quantities. If you lose, let's say you have one Cn minus that reacts, how much HCN and OH minus are formed? Like 1 molecule of Cn minus reacts with water. How many molecules of these do we form?
1.
1, yeah, 1 each, right? It's math, right? You lose one of these, you get one of these, one of these. That means that we can now put a variable x to this. If you lose x Cn minus through reaction, you gain x and gain x here, right? So basically our final Cn minus concentration will be 0.10 molar, but losing by x, some amount. By losing that amount through reaction, we then gain our products. We gain x amount of OH minus and x amount of HCN. So far, so good? So far, are you guys with me? Make sense? Any questions? All right, so basically we now have a math problem that we can solve. We have x on one side and a constant on the other. And this is a quadratic equation. We can solve this directly. X squared over 0.1 minus x equals 2.04 times 10 to the negative fifth. I am going to write that again real quick up in this corner because it's getting a little cluttered now. And that is going to be equal to 2.04 times 10 to the negative. All right. Now, I believe I mentioned this a while back, but we can simplify this equation for ourselves by removing this x. And does anyone remember why we can do that in certain cases? I'm not sure if Angelina was here for this. So it's good to review this. Because Larry says because x is close to 0, and he's exactly right. X is
Because
yeah.
x is very small, so we can
X is
ignore
very
it.
small. Yeah, that's also a very good way of putting it. X is very small, and we can kind of predict, right, that x is going to be very small. You have 10 to the negative fifth over here. X is going to be some small exponent. So compared with 0.1, it's going to be a very small chunk of 0.1 that you're very slightly taking out. It's like 0.1% of the 0.1 you're taking out. Therefore, by removing x, you're not actually changing your final value of x by very much. So this is a valid assumption to make. It's an approximation, essentially, so that you don't have to try to bash out your quadratic every single time you do an acid base. You can simplify the question a bit for yourself through a tiny assumption. And this is a more fine detail, so it's okay if you guys don't remember this, but the way we determine whether this assumption is valid is by looking at these values. Is the power of 10 separated by more than 3? If so, it's going to be a valid assumption to remove that minus x. If it's less, if it's like 2 powers away or 1 power away, then your assumption is no longer going to be so valid. You're going to have more of 5% error or 10% error on your X value, and that's not something you want. In this case, though, we have 10 to the negative first versus 10 to the negative fifth. That's 4 difference. This assumption is going to cause basically 0 change to your final value of X. All right, now let's put all those assumptions into play. Now we just have X squared divided by 0.10 molar. That's going to be equal to 2.04 times 10 up negative fifth. Now, if you guys still have those calculators, take a gander at this question and give it a whirl. I'm gonna solve it myself right now. Let me know when you guys get an answer for X. Do you guys have calculators? Just want to make sure. All right, wait, hold up.
0.014.
0.014. Yeah, that's what I got. Angelina, you're putting in 0.045 something. It's basically it's just 0.1 multiplied by 2.04 times 10 up negative fifth.
So it's 2.04 times 10 to the negative 6, right? So
Yeah,
then,
that's what you get.
so then you take the square root of that. In my
Yeah.
calculator, I don't have. Oh, you know what I did? Never mind. Because the computer doesn't let you separate. So then it read 10 to the negative 3 times 2.04 instead of 10 to the negative 3 times separate 2.04.
Okay,
Never mind.
okay. Yeah, that's fine. No problem. Wait, actually, Amos, can you say what you got again? Your value for X?
I did something wrong. It's 0.14, right?
No, I got 0.00.
No, 0.0014. Sorry.
Yeah,
There's two zeros.
0.001428, blah, blah, blah. All right, let me write that down real quick. All right, in general, this is minor detail. We're not gonna really talk about sig figs too much. That's more of like a thing you learn in AP Chem. It's very technical and stuff. It's not very
There's 3
smart.
sig figs here.
Yeah, 3 sig figs. The thing is, there's actually 2 sig figs, but honestly, it doesn't matter as long as you get an answer close to one of these final answers. Then you just choose the answer. It's not even a problem. If we were worried about sig figs, I'd probably put 3 sig figs here. So I'm just gonna put that 0.00143 molar. Now, what the heck was this value again? What was X again? Someone remind me. What does X signify here?
The molarity of H plus and Cn minus.
Molarity of H plus?
Or isn't it the concentration of H plus? Sorry.
Not exactly H plus. You're on the right track. It's down
Oh,
here.
OH minus and HCN.
OH minus.
Yeah,
OH
I was
minus and
looking at the wrong
HCN.
thing. My bad.
Yeah, no problem. OH minus or HCN, but the thing is the OH minus part is the valuable part, right? HCN, no one really cares how much HCN there is. It's just another compound that happens to be involved. We're looking for pH. So OH minus is going to help us get there. And that's where the whole relationship between OH minus and H plus is so useful. Knowing OH minus, we should be able to determine H plus concentration right away. How do we do that again? Someone else want to remind me?
Isn't that with like the whole the KW thing?
KW, yeah, exactly, KW. This relationship equal to KW, which is 10 to the negative 14th. So basically, you just take 10 to the negative 14th, divide your OH minus concentration. So what I'm getting for H plus is, that is 7.00 times 10 to the negative 12. Does that make sense? That kind of makes sense, right? OH minus is approximately 10 to the negative third-ish. So yeah, 7 times 10 to the negative 12 makes approximate sense. All right, and how did I convert to pH again? This is just make sure you guys know this. How do you convert H plus to pH?
Negative log.
Negative log. All right, now let's do that. Negative log of 7 times 10 to the negative 12 is, drum roll please. Hopefully you guys are doing that. 11.15. Our final answer is going to be D. All right. That's the question. That's question 32 on, I believe that is 2019 local round, USNCO. All right, we definitely took a long path around this question, taking it very step by step. So of course, that's why it took so long. And in reality, this question might be 20 seconds max for the experience.
Wait, how would you do this in 20 seconds?
Well, let's demo real quick. All right, reading the question, I glance at the numbers first. Glance at the numbers, glance at the compounds, that takes me 2 seconds. NaCN, that's just means CN minus to me. HCN, we have that right away. Okay, so first thing I do is calculate CN minus. Maybe not 20 seconds, I might exaggerate. I might have exaggerated. A minute max. All right, I have the KB. KB, I know that's just x squared over whatever that concentration is, 0.1. Multiply that, square root. I have my OH minus concentration right away.
Are you showing work on screen?
No, I'm just typing on my
Oh.
calculator. 14 plus log ants is 11.15. I'd spend maybe 5 more seconds to check my work and then I'd be done. Of course, then after I'm done with all the question, I go back and more rigorously check the stuff. But bottom line is, this is the long way of going about this question, but soon you'll get into a rhythm and you'll know exactly how each question should be approached. Anyway, I was looking to get to other questions, but as always, I overplan. I'm gonna clear those. Anyway, the recording will be out soon, so you guys will be able to see all those notes in another fashion. Very quickly, I just want to see what other questions I have here for us to look at. This one's solution's a little bit different. This one's terribly difficult. This one's probably one of the most difficult questions that they ever had. Also, it was 2018 local round. It was, wow. This one's okay. And then we have this graph. Anyway, I think we will do some bio next week. So we won't get to these questions right away, but I think we'll take a look at some of these other ones and talk about them. They're all acid-base related. Not this one. This one's not acid-base related, but the other ones are. And we'll get to them in time. And anyway, next week's gonna be bio stuff. I do want to ask for anyone listening who wants some bio thing, can we do some AP bio prep? Yeah, sure. We can talk about some AP bio stuff. The thing we talked about last week, cell transport. So like the pumps, the diffusion, all that. That is also AP bio. It's actually quite a big topic on AP bio, surprisingly. I think surprisingly. But anyway, so I know Amos is here for the chemistry. Hopefully, bio's not too boring though. Larry and Angelina, is there any bio topics that you want to focus on?
USABO.
Yeah, anything specifically in the USABO though? Any specific concepts for
Genetics, plant stuff, like that makes up 50% of the test.
the random plant stuff, huh? Maybe something different because I know Larry's going for AP bio stuff and plants don't show up on AP bio.
Cellular respiration,
Oh, yeah,
photosynthesis.
we can talk about cell res. Or we can do plants. Larry says he's good with plants.
Or genetics or something like that, I guess.
Okay. I'll pander something around. I'll choose one of those and we'll go with that. Anyway, yeah, that wraps us up for today. Hopefully this question was interesting. Learn something new maybe. And yeah, I'll see you guys next week, hopefully. All right. Thanks for stopping by.
Well,
Thank you.
Bye-bye.